Welcome to a video on how to determine the domain of a vector-valued function. The domain of a vector-valued function is the intersection of the domain of f of t, g of t, and h of t when the vector is expressed, as we see here, as a sum of the unit vectors I, j, k, or as we see here, expressed in component form. Of course, if the vector-valued function only has two components, the x component and the y component, we'll only be looking for the intersection of f of t and g of t. Let's go and take a look at a couple of examples. Here we want to find the domain of the vector-valued function r of t. There's only two components. We have to find the domain of natural log t plus 1, find the domain of the square root of 4 minus t squared, and then determine the intersection of those two domains. Now, if you know a lot about your basic functions, it helps finding the domain, but I have provided the graphs of these functions to help us determine the domain. Remember, the domain refers to all of the possible values of t in these given functions, where t would be the values along what we normally call the x-axis. So we're really asking ourselves, how does this function behave moving from left to right? Well, we can see here that the domain of natural log t plus 1 looks like it goes from -1 to positive infinity, which is true, but it does not include -1 because if t is -1, we have natural log 0, which is undefined. So the domain for natural log t plus 1 would be t greater than -1. Or if we want to express this using interval notation, it would be open on -1 to positive infinity. And now for the square root of 4 minus t squared, we know the number underneath the square root must be greater than or equal to 0. So we could set this up and solve it as an equation where 4 minus t squared must be greater than or equal to 0. But when t is equal to 2 or -2, we would have 0 greater than or equal to 0, which is true. So looking at the graph, these two endpoints would be included in the domain of this red graph. So the domain for this function would be where t is greater than or equal to -2 and less than or equal to 2, or interval notation would be on the closed interval from -2 to 2. Now we want to graph these two intervals on the same number line and determine where they intersect. So for t greater than -1, we'd have an open point on -1, arrow to the right. And for this interval, we'd have two closed points, one on -2 and one on +2, and the interval is between. So it would look something like this. The intersection would be the values where it's graphed both in blue and in red. So we can see from the graph the domain of the given vector-valued function would be the interval from -1 to +2, where it's open on -1 and closed on +2, or we could say where t is greater than -1 and less than or equal to +2. Let's take a look at another example. Here we have an x, y, and z component, so now we need to determine the domain of all three of these functions and then determine where they intersect. So the first function is natural log t. Again, we can see it graphed here. Again, t can't equal 0, but t can be any value larger than 0. So we have t greater than 0. Using interval notation, we'd have the interval from 0 to infinity, where it's open on 0. Now for the square root of t plus 2, again, we know that t plus 2 must be greater than or equal to 0, so we could subtract 2 on both sides to get t greater than or equal to -2. We can also see that here from the graph. So we have t greater than or equal to -2, or we could express it as close on -2 to positive infinity. And then our last function, we have cosine t. And if you look at the graph, this graph is moving left and right forever with no breaks or holes. And that tells us that the domain of cosine t would be all real numbers, or from -infinity to positive infinity. Let's go ahead and graph all three of these and see where they intersect. So in blue we have t greater than 0. Look like this. Next we have t greater than or equal to -2. Would look like this. And then in green we have all real numbers, which would be the entire number line. So we're looking for all the numbers that are graphed in blue, red, and green. And you can see that it happens when t is greater than 0. Therefore, the domain of this vectored valued function is t greater than 0, or using interval notation, we could express it from 0 to positive infinity, where it's open on 0. Okay, that's going to do it for this video. I hope you found it helpful.